All right, AP Calc kids, we are ready for section 4.4. This is an introduction to related rates. If you talk to previous calculus students, I can tell you that this is not one of their favorite topics. But we'll see. This time the curriculum that we're using breaks it into a couple different sections. So maybe that'll make it a little bit easier for you to wrap your brain around. It's kind of an interesting situation because in these problems, they're word problems. Nobody likes word problems. But on top of that, there's usually there's just one dimension that's changing when you're looking at the problems we've done up to this point. And in this case, you're going to have two dimensions that change at the same time. And you'll see what I mean. So, like for example, when you blow up a balloon, think about a balloon, right? You blow up the balloon, what's changing? Well, the volume's changing of the balloon because the more air you put in there, the bigger the volume is. And the other thing that's changing is the radius because it's getting larger. So there's two values within your formula that are changing at exactly the same time. And so that's what these related, if you wrap in your brain around what the concept is, that's really what it is. So many variables have a familiar relationship. In other words, a way variables are related to each other. A great example is the Pythagorean theorem. And we know the Pythagorean theorem, it's a squared plus b squared equals c squared. Well, if I'm looking at some kind of a right triangle, right? This has to be Pythagorean theorem only works with a right triangle. Let me draw a right triangle over here. The way that we're going to look at this isn't necessarily, because it's going to make more sense to us to use different variables, but the concept's the same. So my horizontal values are going to be x's, right? Makes sense. My vertical values are going to be y's. And if I'm using x and y, I might as well use z for the hypotenuse. So most times we're going to see it with those variables, not the a's, the b's, and the c's. But as I show you these first couple things here, we're going to show you both ways for it. So if in this case, my Pythagorean theorem would equate to x squared plus y squared equals z squared. Same thing. Let's say a triangle's dimensions are changing. This means a dimension, A, B, or C, X, Y, or Z, has a rate of change, and this rate is related to another dimension's rate of change. So in other words, say here's a classic problem they use. This is a ladder that is leaning against a building. If I pull this end of the ladder out, what happens? This end of the ladder comes out, right? I'm pulling that ladder away. Now, this ladder is then sliding down the building. So I can see that I've got a couple dimensions that may be changing here. The length of the ladder doesn't change, but this is still my x, this is still my y, and this is still my z as I'm pulling this away. So when I go to, this means the dimension has a rate of change. This rate is related to another dimension's rate of change. Differentiate your relationship with respect to one specific variable. This is like implicit differentiation. Usually it's with respect to time, but not always. So here's what he's saying. Take the derivative of this. If I take the derivative of the Pythagorean theorem, the 2 comes down in front. I have an a. But every variable with related rates could be changing. And so you're going to say dA over dt. Whatever variable you've got after you take a derivative, whether it's x or not x. Remember back in the day with implicit, if it was an x, you didn't have to say so. But with these guys, you do. Then it's going to be, bring the 2 down in front for the b, 2b dB over dt equals 2c times dc over dt. Now if I did it with the x's, it would be the same thing. With my x's, by the way, they're saying that it's usually with respect to time, but it may not always be with respect to time. That's the dt part. In this case, we're just going to keep it consistent with dt's. This guy over here would be a 2x dx over dt plus a 2y dy over dt equals a 2z dz over dt. Now some of my savvy students, because I know you're savvy, some of you might say, yo, everybody got a 2. Can I cancel out the 2's? And the answer is yes. Yes, you can. So really, you could make this, let me just do it to this one. Same thing will apply to this guy, because this is the one that we're really going to be using. So if I take all my 2's away, divide everybody through by a 2, it's really an x dx over dt plus a y dy over dt equals a z dz over dt. All your 2's can cancel out. You divide them out. They're gone. That's only because everybody has one, so you got lucky on that. So here's an example. A police car approaching a right-angled intersection is from the north, here's my police car, is chasing a speeding car that has turned the corner and is now moving straight east. So the police car's coming this way. The speeding car's going this way. Set up a relationship and then find an equation that shows the related rates of the vehicles with respect to time. All right, well, I need to give variables to this picture. So my horizontal is going to be my x, my vertical is going to be my y, this is my z. I can see that it's Pythagorean theorem. And so we just did the work for that over here. Technically, let me just write what we were using. X squared plus y squared equals z squared. That's the basis for my formula, for my problem here. I know when I differentiate it, I'm going to get this. I'm going to get an x dx over dt plus a y dy over dt equals a z dz over dt. All right, one thing that's going to be interesting to note, this is how x is changing. It's whatever your x value is times how x is changing. This is your y value times how y is changing. This is your z value times how z is changing. And if I think about, just for logic now, set up the relationship, then find an equation that represents the related rates with respect. This is it. This is your answer to the question. But just for the fun of it, looking at my x value, this guy that's in the speeding car, my x values are going to get larger, right? They're going to get larger as he speeds away. So my change in x is going to be a positive value in this situation. Every situation is different. But my x's are getting bigger, so that's going to be a positive value. But check out my y's. My police car, my y values here. What's happening to my y values? They're getting smaller and smaller and smaller. They're decreasing. And so that means that my change in y should be a negative value. They didn't ask me that in the question, but it sure is nice to make note of that because it's going to come up eventually when we start really getting into these problems. So if your value is decreasing, then you're going to use a negative for that. If your value is increasing, it's a positive. All right, here's the last note example. An airplane, point A is an airplane, is flying on a horizontal path that will take it directly over an observer at point O. So the plane's going, it's going to take it directly over this observer. Ooh, I had a right triangle. The airplane maintains a constant altitude. Well, altitude is this height. Again, we're going to call it the y value, and this is a constant. That's going to kind of be nice to us in just a couple minutes. The airplane maintains a constant altitude. Relate the rates of change of the distance between the observer and the airplane and the horizontal distance between the two. All right, so again, I've got a right triangle. I am doing a Pythagorean theorem. This is still my x value, even though it's at the top, it's a horizontal value, and this is still my z value. So how would you come up with the derivative for this? You would again use your Pythagorean theorem, x squared plus y squared equals z squared. And in our case, we saw how the 2's cancel out when I take the derivatives. So now I'm at x dx over dt plus a y dy over dt equals a z dz over dt. Gotta love Pythagorean theorem. And you say, yo, I'm done. I came up with the equation. And I say, no, there's more. And here it is. Here's the deal. If I have a y value that's constant, I'm actually even going to change colors. This guy's constant. If y is constant, then what do you know about dy over, I'm going to put a therefore. What do you know about the derivative of y? If y is constant, then the derivative of any constant is 0. And 0 times that constant zeroes out that whole term. The whole term is gone. So, final answer for this, believe it or not, is x dx over dt equals z dz over dt. That y got knocked out because its derivative is 0, and that just turns that whole term into a 0 term. Maybe I'll say that right here. 0. It zeroes it out. All right, so we're going to try a couple problems from the practice problems. So if you flippy-do, the first one that I thought was a little challenging just because of the wording of it was number 3. So we're going to look at number 3. A spherical balloon is expanding. Here's my balloon. Relate the rates of the change of the surface area with the rate of change of the radius of the balloon, if I could speak. And they give you an area formula. So it's all about the derivative for this thing. If I look at my balloon, this is the area. The rate of change means the derivative. So they're asking me for the rate of change of that area. Well, they gave me the formula, find the derivative. And you say, okay. I'm not going to call it a prime. I'm going to call it dA over dt because that's just what we call the derivatives in these sections. And so find me the derivative. Now remember, pi is part of your constant. It's part of your number. It's not a variable, so you don't need to take the derivative of pi. It's just a number value. So my 2 comes down in front, joins up with the 4. They become 8. And I still have my pi because he's part of the constant. But if I took that derivative of r squared, it's now just an r. But I took the derivative of a variable, so I'm going to say so, dr over dt. Anytime you take the derivative of any variable, you're talking about what it is this time around. Folks, that's the answer. That's it. Done. So although the question's really easy, the wording of that I thought was a little bit off. All right, second one I want to do is number 4. The water level is dropping in a cylindrical tank because of a small leak in the tank. Relate the rates of change between the water level and the volume of the water. The volume is pi r squared h. Well, I have a cylinder, right? A lot of times if you take a look at the picture, cylinder's like a can. Right, here he is, my can, and it's got a little leak in it, got a little hole. It's dripping out water. So the water level is going down. Relate the rates. My volume formula is V equals pi r squared h. And I'm supposed to find the derivative of that. And guess what? You have the ability. This one is going to be like a product rule. And the product rule goes with pi r squared as the first term and h as the second term. So we're going to find dv over dt. I'm going to find the derivative, but I have to use the product rule to get there. All right, so first times the derivative of the second. That's going to be pi r squared. Derivative of the second is dh over dt. Technically, the derivative of h is 1. So it's 1 times that dh over dt. I'm taking the derivative of a variable. Every variable, you have to say so. All right, plus product rule. The second, h, times the derivative of the first. Well, 2 comes down in front. 2 times pi is 2 pi. The r goes to 1 less power, so it's just an r. but I took the derivative of a variable and I need to say so, dr over dt. Now when you're done, what you need to do is like what we did back here in this particular problem. This is going to come up in several of these practice problems, that one of the pieces is actually constant. So you want to check to see if you've got any parts of this that are staying constant. Any of the variables in the problem that are constant. So let's go back here and think about this for a minute. All right, so if I'm looking at my first thing, the first variable I have is my r. Is the radius in my cylindrical tank here changing at all? The radius is constant. You see how that works in this thing? So I know that r is constant. R is constant. And my h is the other variable involved, the height. That's the height of the water level. Well, that does change because it's going down, right? It starts out, you got the leak, it's slowly losing water, and so the height does change. So I can't do anything with that. It's the r piece, the radius, that's constant. Well, if the radius is constant, its derivative, dr over dt, equals 0. How does that affect your formula? All right, so if this is the case, then that equals 0, which means its whole term equals 0. Everybody with it becomes a 0. So the final answer for this guy is dv over dt equals pi r squared dh over dt. And that's your final answer. So in the end, you want to double check yourself and see if anybody's a constant. If you do have a constant in there, it totally zeroes out the piece where the derivative is for that, since the derivative of a constant is 0. So that was number 4. And then I'm going to stop with number 6 is my last one, because this one gets into some trig stuff. And again, I know you love trig so much. Number 6. A rocket is rising vertically. An observer on the ground is standing a certain distance from the rocket's launching point. As the observer watches the rocket, the angle of elevation is increasing. Relate the rates of change of the angle of elevation with the speed of the rocket. A lot of times a picture of these things is really helpful. So if I think of a picture of this guy, I have a rocket. Can you draw a rocket? I'm not the best drawer. There's my rocket. My rocket is going up, right? And I've got an observer over here. Here's my observer. I'm going to give him some hair. Okay, there's my observer. He's over here. Right? And so I know, look at what I'm drawing. Check him out, Mr. Right Triangle. This one's not going to be a Pythagorean theorem one, though, because they want to know how the angle of elevation is changing. Well, the angle of elevation is the angle when you're looking up at something. That's this guy down here. This is your angle of elevation. And so I'm thinking, well, geez, if I can't use Pythagorean theorem, then what can I use? And I'm relating the rates of the height of this rocket. That's going to be, I'm going to call it y because that's a vertical value. And this guy is standing over here x feet away, or a certain distance away, whatever it is. What can I use to be able to relate those two things? What formula can I use? Again, I can't use Pythagorean theorem. They didn't say anything about the distance between the guy and the rocket. So the only thing I've got are my trig functions. Back to right triangle, SOHCAHTOA. So if I SOHCAHTOA thinking on this, I have this guy's my opposite side. This guy's my adjacent side. And so I need to relate those two things. SOHCAHTOA, it's my tangent. I know the tangent of that angle has to equal the opposite over the adjacent. Relate the rates. Well, they don't want the formula, do they? They want the derivative of the formula to relate the rate. All right, so derivative of tangent Ooh, do you have to go to your card to see? Is secant squared. But check this out. This is like a variable, and so I need to literally say, just like I did with the other ones, whenever you take the derivative of a variable, you have to say so, d theta over dt. So the left-hand side of this becomes secant squared theta d theta over dt when I take the derivative on the left. If I take the derivative on the right, oh my goodness, I have to Hody-Hi. I have to Hody-Hi this thing. And so if I Hody-Hi it, now there's more than one way to do it, but the way that I'm looking at it, it's definitely a quotient type thing that I need to Hody-Hi. So the bottom times the derivative of the top. Well, the derivative of the top is dy over dt minus the top, y, times the derivative of the bottom, dx over dt, over the bottom squared. All right, and I'm looking at this and I'm going, oh gosh, that's ugly. But let me pull the trick again of, is there anything that's constant? Maybe I can make this a little bit better. So I'm looking at my picture. My y is changing, right, because that's the rocket moving. But how about the distance away that this person is? That x value, he's not going anywhere. He's just staying the same place. So I know that x is constant. And if x is constant, then dx over dt equals 0, which means that this whole piece is a big fat 0. And so here's what I'm at next. The secant squared theta d theta over dt equals an x dy over x squared. I'm sorry, dy over dx. I write this bad. I'm getting so excited because I know what's coming next. X dy over dt over x squared. Well, I have an x over an x squared, so what can you do with that? You can cancel. That gives you an x on the bottom. So here's the prettiest I can make this thing. Secant squared theta d theta over dt. Thanks God this is the end because I don't have much room. The x over x squared becomes a 1 over x, and then you have a dy over dt with it. So let me see if I can kind of, I don't normally box because we don't like to box in AP, but just so you can see my answer. And that, my friends, is your answer to number 6. So again, that brings back the SOHCAHTOA stuff that you haven't seen in a bazillion years. But there it is. So you are working on, this one does have some test prep questions. Actually, it just goes to number 9. So have at it. Shoot me an email if you've got any questions, and I will see you in class.